Today we are going to discuss regarding the technology which we are applying in CO2 laser cutting machine. Already you have an experience in our lab how this functions, how it's principally working. Let us get into the fundamentals. I hope all of you are quite aware of what a laser is and how it performs. But still, just to recapitulate, our educators. So we are taking this session as a recapitulation of the ideas of what laser is and how it functions. The fundamental aspects of laser. Let's get into this. So laser beam is basically the acronym term used for laser amplification by stimulated emission of radiation, and this is a thermal process where the thermal energy is used on materials of any melting point, and it can be used to melt and vaporize the material instantaneously. Because the temperature rise takes place with the incident laser helps in melting any substance instantaneously. So there is a thermal energy associated with it, and it melts the material and instantaneously vaporizes. So based on the conversion of electrical energy, where it is being used to generate the laser source, and finally the light energy is being taken into account for converting the electrical energy into the source of laser to deliver on the work surface as thermal energy. So over here you can see that a laser which is incident from the laser head on the work material, it melts and simultaneously gets vaporized. Now laser, we call it as a beam. So when a beam is being incident, so it has to be focused through multiple reflections. Okay? So these lasers are reflected through mirrors. Okay? So these mirrors help in targeting the work surface at a specific point. Right? So the reflecting mirrors which actually receives the laser, and they help in working on the surface to be machined. So it can be machining, it can be welding, it can be removing of say substrate from the work surface. Like for example, if there is some residue or if there is some deposition on some metal surface in terms of say rust, okay, or let's say on a copper plate, sometimes you find that due to chemical reaction there is a deposition on the surface. Okay. Maybe it can be a painting, or it can be some motif on a copper plate, and there are some oxide layers which are sometimes fall on the surface of the layer of copper plate. Sometimes you need to remove it, right? So physical removal of those fine layers are quite challenging. So the alternative method is using laser. Okay, you can use laser to remove that small amount of layer which might be in microns, that can be easily removed. It can be copper, it can be ferrous materials, any surface. That laser removal is very much useful nowadays in restoring. Sometimes we have some metallic artifacts which have been contaminated with this oxide layers, and with the help of this laser, it is very much effective in removing the surface, or cleaning of the surface. So it's called laser cleaning, which is nowadays very commonly used in preservation of artifacts. And apart from that, we know that lasers can be used in medical domain to a large extent. Like one such example is in the laser of removing of cataract. Okay, so the laser surgery is very much useful nowadays in medical terms. And obviously in mechanical domain, it's a huge, this laser has given impetus in developing and removing, machining, welding. So you name it, and there are opportunities of laser. So the laser beam is highly intense in nature and it is monochromatic, unlike the white light that we have over here in our atmosphere. So it is highly powerful and capable of propagating to long distance without diffraction, and they are not easily absorbed in water. So it is directional. It has a directional property. So this light energy from the laser to remove material through vaporization and ablation. Okay. So it is concentrated optically. So what we do, basically there are some flash lamps which are called exciters. So these exciters actually excite the material, and that excitement of the material results in release of ions or electrons. So now those electrons, when they are released from the molecule, they move in a Brownian movement, and those molecules they tend to move around in that chamber, and that gets connected with the mirrors. One is a completely reflecting mirror and one is a partially reflecting mirror. And in between those two parallel mirrors, multiple reflection takes place. And the number of times these electrons get reflected, their energy level slowly increases in many folds. And finally, what they do, they also disturb the other molecules in their vicinity. So from one electron being released, it creates the disturbance to the neighboring molecules in that area, and thereby more and more electrons get released in the system. And finally, what happens? Few of those electrons have a chance of coming out from the partially reflecting mirror, and when it does, they are being channelized and concentrated and focused on the work surface or LD, and eventually the materials get removed. So basically, these are charged particles, and the energy related to these charged particles are from the electrons, and these electrons are having orbitals, and the outermost orbital having the electrons, they actually take part in the process of laser emission, because the exterior or the outermost layer of this energy band or orbital, that electron normally have a chance to get released with the external source of excitation. So in the ground state, the electrons are very much stable in their energy band, and their stability actually have the lowest energy level in the stable state. Now, after absorbing the external excitation, the electrons on the outermost energy band have a chance to release itself, or the prior to the outermost layer, the layer which is next, the electrons will jump to the higher orbital. So that excitation actually create the electrons to shift their position from one energy band to the next energy band, or from one energy level to the next energy level. Now, in doing so, either they become stable in the higher energy band, and if they are not, then they will try to fall back to their stable state. Okay. So when they are falling back from the unstable higher energy band to the lower energy band to access the stability, they release energy. When they are falling back, then only they release energy. But when they are absorbing energy, they accumulate their energy to move on to the higher energy band. So in normal condition, electrons present in the atoms are in the stable state, in the ground state, but the external energy provided to the atoms for excitement of the electrons, they actually help them to move to the higher energy band or the higher energy level. And they try to remain in the higher energy level, but during a very short span of their stay at the higher energy level, they try to emit photons when they fall off to the lower energy level. So this process is basically called spontaneous emission, the release of photons by the electrons when they are jumping back or falling back to the lower energy band. It is called spontaneous emission. So this is what happens. You have the atom, and they are the different energy band of the electrons or the orbitals, which we term it as. So when the excitement is given to a certain atom or it is being received, the excitement is received by the atom. So the electrons in a particular orbital try to move to the higher energy state or excited state from the ground state, and they try to remain stable at the excited state or the higher energy band state. But if they do not find it stable, they will always fall back to their ground state. Okay? So in doing so, they release the photon or the emission of photon takes place. So electrons from the higher state may not come directly to the ground state or the lower energy state. In between, they come to some intermediate state, intermediate level for few microseconds, and then they come back to their ground state. So during this period where the electrons have energized and moved to the higher energy level, and they are falling back not to their original ground state but some intermediate state, and then they are coming back to their original ground state for stability. So it is actually known as the lifetime of that energy state. Okay. So lasing action takes place with the help of the photons that are being released. The accumulated photons that are being released by the electrons when they jump back from the higher energy band to the lower energy band or the higher energy state or excited state to the ground state. So that actually results in emission of photons, and one photon, when it is released, it creates disturbance or ripple in the entire system of the material, be it a gas media, be it a ruby crystal or some other materials which have the capability of lasing action. So the whole system slowly gets excited, and the photons are released in an avalanche form. That means millions and millions of photons get liberated in this process of excitation, and the entire system is capable of producing laser. So this is called the lasing action. So over here you can see from the ground state or from the stable state, the energy level, or these are the various energy levels of the electron orbitals. So from the ground state or the steady state, it is being excited to the higher energy level, and then when it doesn't find it stable or stability at the higher energy level, it falls back to its intermediate state, and from there it comes back to the original ground state for stability. Okay, so not all the materials are basically having the capability of lasing action. Very few materials have this capability, like ruby crystal, which is basically aluminum oxide or alumina, and other Nd:YAG material is there, neodymium dope, yttrium aluminum garnet. Then we have gas lasers. Okay. So these are some of the common materials which are capable of producing laser rays. Okay. So when the electrons, as we have seen, that they are excited to their higher energy band and intermediate level they attain before falling off to their ground state. So it is called the metastable state. Okay? When the electrons are coming to the intermediate level, which is called the metastable state, and when the photon is coming from the metastable state to the ground state. Okay? So in that period, it liberates photons. Okay. So this from one photon, the energy level gets multiplied. How? So this single photon which is being released when the stability is not attained by the electrons at the higher energy level, it strikes its neighboring atoms, and that atom again performs the similar trend of getting destabilized. That means its electrons also move to the higher energy level and then it falls back. So there is another liberation of photons. So from one photon, two photons get liberated and so on and so forth. It gets multiplied in n number of photons, and finally the laser rays, the beam of the laser gets developed through this system of excitement of the material. Okay. So over here you see when an incident photon strikes the neighboring molecule or atom. So the same thing happens over here. The excitement reaches the atom and the electron moves from energy level 1 to energy level 2, from the ground state to the higher energy level or the higher energy band, and then it does not become stable at the higher energy band. It falls back to its original ground state, and in doing so again it releases in a photon. Okay, so from one photon there is an emission of two photons, and this way it gets multiplied into multiple number of photons. Okay, so the excitement propagates in the entire material of the work surface, and slowly more amount of photons are being released, okay, through this excitement, and this accumulation of photon will result to the development of your laser. Okay. So we have the electrons at the ground state and it is elevated to the higher energy level, okay, in the excited state, and they do not remain at the higher excited state, then they fall back to its intermediate metastable state, and then they fall back to this is the higher metastable state. Then we have another state which is called lower metastable state, and then comes to the ground state or the stable state. So this is basically called simulated emission. Okay? So this phenomena is termed as simulated emission. So this excitement of the electrons get propagated and the lasing action continues. So this laser beam, when it is incident on the work material, it releases energy, and that energy is capable enough of melting and vaporizing any work material. Okay. So what we require a high voltage power source to have an exciter, which is our flash tube. So a capacitor is used to operate with the flash tube, and this flash tube actually emits the photons, which actually excites the material on which the lasing material on which we are working with, and necessary energy is getting released for this. So this emission of the photons from the flash tubes actually help in targeting the molecules or the atoms, and the movement of the electrons from the energy level, changing of the energy levels from ground state to the higher energy level continuously takes place, resulting in spontaneous emission of photons. Okay, and this actually results in emitting the electrons continuously, which actually increases the strength of the laser. So more and more of the emission of electrons help in more liberation of laser rays, and sometimes we say that the intensity of the laser ray has to be increased. Like in yesterday's work we have seen, in order to cut the material we need more intensity of laser. and let's say for etching purpose we need to have less amount of laser intensity. So this increasing of intensity of the laser depends upon how much emission of electrons are taking place. So the phenomena is taking place in a nanosecond time, but the effect can be observed as the workpiece which can be cut or it can be etched depending upon the intensity. So hardly we can feel the difference, but in the background, in the very short span of time, this phenomena is taking place. The liberation of electrons, more and more we are increasing the intensity manually with the help of these machines, but the effect which we are getting is the intensity getting increased to cut the material. That means more energy is being liberated by the lasing material, and that actually helps in cutting the material of a larger thickness. Okay. So that is how we develop the working phenomena or the working parametric combinations for removing or working with the laser. So in the beginning, again, we can find that in the beginning the energy that is there is in the ground state. That means all the electrons and atoms thereby are in ground state or the stable state. It is only when we excite the material and then the emission of photons takes place. So the light waves inclined to the axis of the crystal will leave the box within a very small span of time. When you are exciting the material within a very small, you will hardly know the difference, because the moment we switch on the machine, the excitement starts. In our case, we have a CO2 laser cutting machine. So the moment we switch on, the lasing action starts. That means the lasers are activated, and when you are operating with the machine, instantaneously the laser is incident on the work material. Okay. So there is a very less, there is no lag between development of the lasing, the laser energy and working on it. Okay. There is no lag practically. So it is a continuous process. The moment you give the electrical energy to the lasing material, instantaneously the lasers are produced. Okay. So that will help in working on the work surface instantaneously. Now the question comes, what will be the intensity? That depends upon the excitement. If you are wanting a low intensity laser, that means the excitement will be reduced to some extent. If you are increasing the excitement, then more lasing action will take place. That is the difference which will happen. Now the lasing action takes place over here, has been explained through this diagrammatic representation. Now these are the lasing materials on which the excitement is being carried out. So through the flash lamps or other excitement process, we can excite the molecules or atoms inside the material, and they will liberate the photons in the system, which will have a multiple reflection, one through the fixed mirror and one through the partially reflecting mirror. So finally the laser ray will come out through the partially reflecting mirror, and then through the multiple mirrors it gets reflected and it is being applied on the work surface. It will reflect through the partially reflecting mirror and it will come out through the aperture, and through the mirrors it will be focused on the work surface. Okay. So the materials can be removed, welded, cut, and multiple operations can be performed depending upon the nature of the work. Okay, so drilling, cutting, grooving, many things or many operations are performed. Now, certain things happen when the laser is incident particularly on material, that means metal. Okay. Now, we are working on non-metals, so hardly you will find any difference. But when you are particularly working on metals, so when the laser is incident on the metal, it will melt. The surface will melt. Instantaneously, the surface will melt and vaporize. Some amount will vaporize. The area where the laser is incident, once it is melting, the moment the laser moves away, it will solidify. Okay. Now the thing is, the surface where the solidification will take place will become rough. Okay. Why? Because it will differ, the characteristics of the material which has melted will differ from the parent material. Okay. So that deposition will make a microscopic level of unevenness on the surface. Right. So sometimes this unevenness is detrimental to the workpiece. Sometimes it is not warranted in the design, but still it is happening. So we call it microscopic casting. We call it microscopic casting. Or there is a recast layer. The term is actually recast layer. So this microscopic recast layer actually falls on the work surface in case of metals. In case of metals, this happens. So our objective will be to minimize this recast layer. You cannot avoid it because it will happen, but at least you can set the parameters and the machining performance in such a way that this recast layer can be minimized. Okay, number one. Number two, see, when we are focusing the laser, it is having a tapered effect. So the tip of the laser beam which is incident, it has minimum spot diameter. Now supposing you are going for a drilling with the laser, so the lasing ray will be focused up to the focal point over here. So as you are moving through the depth, so the hole you are creating will have a tapered effect. That is also a defect, we call it in terms of machining. You want, our objective is to make a cylindrical cross section of the entire hole, but if the thickness of the material is large and if your focal distance is not set properly, then you will have a tapered effect in the hole. In case of small diameter hole, it can be neglected, but in case of a large diameter hole, if the focal lengths are not set accordingly, so there will be a tapered effect in the microscopic hole that we are creating with the laser. This will happen. So these two aspects has to be taken care of. One is the recast layer, which needs to be minimized, and another one is the maintaining of cylindricity of the hole that you are creating with the help of laser. Okay, so basically two different types of working action of laser has been shown over here. We have a flash cam over here, and we have a lasing crystal, ruby crystal is given over there, and obviously the intensity of the laser will be determined according to the power that has been supplied, because the lasing action will increase more with the help of the activity of the flash lamp on the UV laser. So more and more materials will get, photons will get liberated, and the lasing action will increase depending upon the intensity. Okay. Now, working of laser beam machining, a very high energy laser beam is produced with these lasing machines. Various types of lasers are there, solid state laser and gaseous laser. We have seen. Now, this gaseous laser we have discussed yesterday, like it is basically used for non-metals, because they are relatively weak in comparison to the solid state laser, and they are not reflective in nature. They do not reflect back. So that is the advantage we are using for this gaseous laser on non-metals, like wood, rubber, polymer, leather. Okay, so this kind of materials are being used for CO2 laser or gaseous laser, and others are being used for metals or working on metals. Okay. So laser beam when strikes on the surface, obviously that is the thermal exchange, the heat generated by the laser on the work surface. One it gets absorbed, one it gets radiated, okay, and another it is reflected. Okay, so we need to avoid that reflection because the lasing head which has the mirrors will get destroyed if the reflection takes place from the surface, and which is very much prominent in case of materials. Okay. See, this is what I was discussing. Okay. So if the focal length is not adjusted accordingly, see you have a tapered effect. You have a tapered effect in case of a hole generated by laser. Okay. So this has to be taken care of. This spot diameter if it is increased at the tip of the laser, the spot diameter is very small. So as you move backward towards the lens, so that means you are decreasing the focal length. So there increasing the spot diameter will take place, and that will result in the tapering action of the laser. Okay. Now the focused beam of laser, which is actually intended on the work surface, will be helping in multiple actions using the lasers. That means cutting action or engraving, or you want to remove the substrate layer on any metal surface. So multiple objectives can be obtained or attained. So three things are required. One is the laser media and is the excitement, providing source, excitation source, and then there is an amplifier which amplifies this excitation, and that actually gives more and more liberation of photons. Ultimately, the laser gets intensified. Okay, so the illustration of lasing action is a focused beam of laser coming through the lasing head, and it is focused through the lens, okay, and ultimately coming on the work surface. Okay, so this is the U is the initial distance from the lens, and this is the final distance from the lens on the work surface. This is the focal length which has to be taken into account for better lasing action. So this is very important, maintaining uniform focal length on the work surface, which actually helps in maintaining the accuracy that has to be obtained while using laser for removing material, for lasing material on the work surface.
Sir, that convex lens only for centerize the all beams.
For material, because we concentrate a huge amount of laser rays and we are focusing or channelizing it to a particular spot diameter. Okay, so the convergence of all the all the laser to a particular point will intensify the energy to a very small spot diameter, and that concentration of the energy to a very small spot diameter will result in rising in the temperature of the material to its melting point and beyond. Okay. So that will help in melting and instantaneously vaporizing the material. Okay. So in metal forming or metal cutting using this energy, three things happen. One is the heat is dissipated through conduction, convection, and radiation. Okay, normally in metal machining it takes place because heat we know it gets dissipated in every direction. So three forms of heat transfer takes place: conduction, convection, and radiation. Over here, using this laser, two things happen over here. One is the conduction and radiation. The heat is conducted through the layers of the workpiece substrate, and some amount of the heat gets radiated into the atmosphere. Now, why this is happening? Because see, there is no contact In normal machining, what we find, there is a cutting tool being involved for metal machining. In normal machining, you have a hacksaw and you cut the material. So there is a physical contact between the cutting tool and the work material. So over there also, in those situations, we will have heat generation. Heat generation takes place, and heat generation takes place through the application of the cutting tool on the work material, resulting in stress development, shear stress development at the cutting tool, and that shear stress development results in temperature rise, along with the frictional force which is being acted at the cutting tool. Okay, two things are happening. One is the shear action taking place, another one is the frictional force taking place. These two results in rise in temperature, and that rise in temperature is decimated or decimated in the work material through conduction, convection, and radiation. So over here, since there is no contact between or there is no physical presence of any cutting tool, so laser itself is acting as a cutting tool. So it has the capability of removing work material through its energy released, and that energy is in the terms of heat energy, which is basically melting the material. So the heat being released through this process of melting, it also gets converted, some amount gets converted into radiation. Okay. So maximum gets absorbed in the work material, the remaining gets liberated through radiation.
Zero pixel, zero shear.
There is no physical contact between tool and work. So entire energy is being expended for liberation of heat. Okay, 90% of the heat gets liberated in the work material and it gets liberated. So any known material can be melted using this laser because the temperature rise takes place to the tune of 10,000 degrees Celsius within a very short span of time. So that is enough for melting any known material on Earth. So this is how the laser is acting. So the laser beam, after getting released from the lasing head, okay, so it gets multiple reflections. So these are the galvanometers which actually help in controlling or angling the laser on the work surface. Then it is passing through F theta lens, the lens that is used for focusing on the work surface, basically an F theta lens. And the lasers are guided through these galvanometers, multiple galvanometers that we use to control the mirrors. Okay, in our machines also there are two sets of mirrors at the two extreme end on the machining zone or the working zone of the CO2 lasing machine. Okay, some of you might have seen. So those two lasers are being controlled by this galvanometer. So they angle the laser and they take their positions or angle them in such a way that the laser moves through multiple reflection and then they pass through the F theta lens, which actually helps in creating or developing the focal length of the laser, and it is incident on the work material. So depending upon the focal length, the intensity increases and the accuracy of the work increases. So if the spot diameter is exactly at the tip of the focal length, so that will create maximum energy, that will liberate maximum energy, and the intensity will be at its highest level, thereby removing the material will be very easy. And also at the same time, the cylindricity of the work material or the hole that we are creating, that will also be retained. The cylindricity of the hole, if you are creating a hole, that will be also retained if the spot diameter is meticulously set. So laser beam machining working material is one such parameter. Type of the working material which you are working with also type of the work material which is also significant in terms of gaseous laser or solid state laser. Then the surface reflectivity. See, in gaseous laser the surface do not reflect, unlike the metals which have the tendency of having reflectivity. So it absorbs the light, non-metals to absorb the light, so there is no reflectivity. And the thickness of the work material is also an important parameter, because more the thickness, more intensity in the laser you have to generate such that the work is effectively removed. Okay. If the thickness of the material is less, so less amount of intensity is required. And next, if you are using some gas, that means CO2 gas, so the concentration of the gas plays a significant role in terms of liberating of electrons. Okay. Now, the type of gas, pressure and nozzle which you are using for generating the laser is also a significant parameter over here. And next is the environment which you are working with. If the environment is humid, obviously it will dampen the entire process. So temperature and humidity also plays a significant role in blazing or generation of lasers. Other parameters are stand-off distance. Stand-off distance is the distance from the this is the stand-off distance from the lasing head to the surface. Okay, so focal length and stand-off distance almost are same over here. So you can call it focal length in terms of the physics terminology. We call it stand-off distance in terms of mechanical terminology. Both are same. Cutting speed, higher the cutting speed can cause taper and degrade accuracy and quality of the cut. So if you are engraving, then cutting speed might be high. If you are cutting it, then cutting speed has to be low, because you need to provide sufficient amount of time to the laser to remove the material. So low speed, okay, low speed, high intensity is provided in case of cutting, and engraving it's the reverse. Gas pressure, optimum gas pressure is to be maintained. Too low can cause improper material removal. Too high can cause loss of heat. Okay. See, if more amount of gas pressures are used, the liberation of photons will be more. Okay. So we have to create the gas pressure or maintain the gas pressure accordingly. So gas laser generation, so we have a lasing tube which has a CO2 laser, a CO2 gas inside it, and we are exciting this gas laser from outside source, and the excitement results in emission of photons, and these photons move along the axial path of the lasing or laser tube, where we have a completely reflecting mirror on one end and another one is a partially reflecting mirror. So after having multiple reflections, the energy level increases in the photons, and finally they are liberated from this lasing tube. So this is another type of laser, Nd:YAG laser, neodymium dope, yttrium aluminum garnet. This is the new type of laser which is commonly being used over here. The same thing happens. We have a flash lamp over here. Another, you have a lasing rod of Nd:YAG material. Okay. Nowadays, YB-YAG is also being used. Okay. Instead of Nd:YAG, YB-YAG laser is also being used nowadays. So the flash lamp actually it excites the material. It's a pump source which is exciting the electrons or atoms inside the lasing rod. So the reflecting of the photons takes place. The phenomenon is same. Okay, whether it's a gaseous laser or a solid state laser, the phenomenon is same. Only the intensity changes. Intensity of the application area using a gaseous laser in contrast to the NDA laser, these are different. These are mainly used in removing materials or metals. Okay, so this is the typical CO2 laser that we have over here. So the laser is being generated by this glass tubes where the CO2 gas is provided. CO2 gas is provided over here, it's sealed in the glass tube. Okay, and high voltage flows to the tube and reacts the gas particles, increasing the energy. So ultimately, the photons are liberated, which are the sources of energy, and high temperature rise takes place when it is emitted on the work material. Okay.
Sir, so there is reason to split carbon dioxide.
Sorry.
Is there a reason to split carbon dioxide?
Reason to select carbon dioxide.
Or other gases?
Yeah. So one thing is that with the excitement, external excitement that has been provided to the CO2 gas, that has seen the liberation of electrons from the atoms are easier compared. And if you see the periodic table, so it justifies your answer why CO2 is used.
Maybe due to inertness of
No,
the CO2.
the liberation. See, if you read the no, if you see the periodic table, the property of the CO2, okay, is justified because the amount of energy required to liberate the electron from its stable state to the higher state is much easy in case of CO2 compared to the other gases. Okay, that's why CO2 is used. Number one. Number two, it is the cheapest gas which can be used for this purpose. Other gases are difficult, H2, hydrogen, it is very difficult to store and capture. CO2 is readily available and the cheapest. This is the major point of accepting CO2 compared to other gases. Okay. And second is it is non-reactive, inertly nature, non-reactive to other materials.
Unless you have the metastable state, laser will not be created.
No.
So maybe one of the different CO2.
That's why I told you that it is the easiest
And
way.
another part is the coherence. One part is basic. Coherence part is very important for this. Coherence and population inversion. So that happens very easily in CO.
Population inversion means you have to have the metastable state.
Exactly.
Yeah, metastable state will be there. When you are exciting the electron, it will reach to its higher energy level. Then it will fall back to its upper metastable, then lower metastable, and then to its ground state. Okay. In this phenomenon, there is an emission of photon. So that liberation of photon, and when it propagates into the media, the multiple photons are getting liberated. It's a spontaneous emission. Okay.
Wavelength is important. Wavelength has to maintain
Well, yes, yes.
phase difference in
Yes, yes,
space
yes.
and time.
Exactly.
That happens for apparatus.
And to be equal to this.
So mirror plays a vital role in focusing the lasers. Okay. So one is a fully reflective mirror and one is a partially reflective mirror. So the multiple reflection takes place through these parallel mirrors, and actually this also increases its energy level. Okay, energy level of the photon. So more and more reflection takes place, more and more energy it attains through this multiple reflection, and finally from the partially reflecting mirror, it comes out from the system, whether it's a solid state or it's a gaseous state, it comes out from the partially reflecting mirror. And final mirror is located inside the lasing head, which actually directs and focuses the laser rays through the f theta lens on the work surface. Okay. So this actually the focusing part is also significant in a sense that the spot diameter plays a vital role. With the larger spot diameter, that means more amount of heat affected zone takes place. If the spot diameter is large, so heat affected zone is also large. So what will happen? Actually, we don't want large surface to get. Okay, so see this become, let's say this is my focal length. Somewhere in between, in case of a hole that I am creating over here, through hole. So see, this actually increases the area of the gut of the material. So more the area of gut on the one surface, more will be the heat affected zone. If the spot diameter, this is my ray, which is incident. So this becomes my spot diameter. So over here you find this is larger. So this will liberate more amount of heat over here compared to this one too. So more the spot diameter, more heat will be generated. So more heat affected zone will be there. So spot diameter plays a significant role over here. So depending upon the focal length, this changes. So we have to adjust in such a way that the spot diameter is uniformly maintained, and finally the cylindricity of the hole, the cylindricity of this hole has to be maintained uniformly throughout. Otherwise, what will happen? There will be a tapered effect of the hole. There will be a tapered effect of the hole. Like this. The hole will be tapered. So making a through hole for a larger cross section or for a larger span of the work material, the thickness is large. So this tapered effect is a possibility. So you need to adjust the focal length in such a way that cylindricity is maintained throughout the entire work area. Okay. And another thing already I have discussed, like the recast layer, because when the laser is incident over here, the adjoining areas get melted and again they get solidified. So microscopic recast layer is there. So again, what will happen? You need to remove the recast layer, right? Which is an additional operation that you have to perform. You remove the material, you make a hollow cross-sectional cylindrical hole. Again, there is a recast layer developed. So again, you have to remove the recast layer through another operation, another time, another money extra you have to apply. So which will add cost to the entire system, entire process, which is not warranted. Normally, in practical sense, what I can tell you, recast layer generally takes place if the material is ductile in nature. If the material is brittle and very hard, recast layer probability of developing this recast layer will be minimum. You cannot avoid it, it will be minimum. But in case of very hard and high temperature strength resistant material, high temperature strength resistant material, high temperature strength resistant ASR, high temperature strength resistant material. Okay, means ceramic materials, composite materials, metal matrix composites, ceramics. Okay, then we have okay, alumina. this kind of materials, they are resistant to heat. Okay, refractory materials are there. Refractory materials, ceramic materials. Okay, we have cubic boron nitride, then diamond. Diamond is also there. Okay. See, these materials are really tough. So, with a normal or conventional machining system, machining this material is really a challenge. So, these are the alternative methods or non-conventional methods through which the machining is possible. So, nowadays, metallurgists are developing newer materials. Okay, graphene is one such material which is very hard compared to graphene. Okay, how to machine graphene? It's a challenge. Okay. So, shape alloy memory materials. These are very hard materials and new materials. So, you cannot use the conventional methodology for machining and cutting these materials. So, what is the alternative way? These are the alternative ways. Laser is another alternative way which can be used for machining these materials with greater accuracy. Why you are using, in spite of the process being costly, why you are using this? Because the post-processing activities are minimum over here. In case of conventional machining, post-processing activities are there, which adds cost. So, in industry terms, if you think that cost is an important parameter as well as time, so minimum possible time should be provided to develop or machine any material. So, you are using a process, then additionally post-processing you are spending some time, that adds cost to the processing time of the work. So, which is not warranted. Okay. So, machining conditions, lasing speed, for deep cutting it should be minimum, and for light cutting it should be high. Power, for light engraving it should be low, for high engraving it should be high. And interval of the laser emission, it should be low in case of finishing, high in case of rough cutting. Scanning, power should be low, speed should be high in case of engraving, and for cutting, power should be high, speed should be low in case of machining. These are the some machining conditions which is set for operation. So, material removal through the process of laser beam machining. So, it is the amount of laser energy which is absorbed. Then there is a rise in temperature in the laser on the work material, which helps in melting and eventually vaporizing the material. Then the material gets removed through the process of melting and vaporization. Now, it can be gas assisted, it can be solid state, through which we can excite the material and we can use that lasing energy to remove the material. So, various types of lasers along with the applications are shown over here. Large hole up to 1.5 millimeter diameter, ruby Nd:YAG lasers can be used. Large hole, 3 pan can be used, Nd:YAG and CO2 lasers. Small hole greater than 0.2 millimeter diameter, ruby Nd:YAG lasers. Drilling, Nd:YAG laser and ruby lasers can be used. Thick cutting, CO2 with gas assisted lasers are used. Thin slitting of materials and thin slitting of plastics, we can use Nd:YAG and CO2 lasers. Plastic, metals and organics, you are using as a work material. See, metals over here are mainly ductile material. Aluminium, then brass. Okay, so this ductile materials of small thickness can be used for CO2 lasers. It is not meant for ferrous materials. Okay, extremely ductile material, that too, the surface should be non-reflective in nature. Okay, so
Lead also.
non-reflective surface, non-reflective surface metals, CO2 can be used. Otherwise, you cannot use CO2. Okay. Then non-metal ceramics, you have so many options: India, pulse CO2, okay, ruby, so many options are there. Okay. So welding is another technology through which laser is very much applied. So joining of two materials, okay, microscopic welding, underwater welding, lasers are sometimes used. Okay, in underwater you cannot use the conventional technology of this gas lasers. Okay, so it is very difficult. So laser for underwater welding is a very helpful proposition for welding. So heat generated, it can be used to rise the temperature of the work material, and the joining action takes place by instantaneous melting and solidifying of the work material. Okay. So the electromagnetic radiation increases on the surface of the base metal with such a concentration of energy that the temperature rise melts the work material and vaporizes it and solidifies it. Okay. So advantages are tremendous nowadays. Most advanced applications in the technology or in the working sphere where the new technologies are being adopted today. So obviously, in spite of the fact the initial cost is high, but still taking into account the wastages are minimum, because with the help of laser, minimum post processing work are being done and wastages are minimum, which is very much essential in industry to minimize the extra cost. That is one such objective the industry is following. So laser provides the accuracy as well as the time with which the processes can be completed. So it is capable of producing very accurate work surfaces, holes, okay, on contours, profiles. So it is having the capability of cutting, engraving any materials, okay, where the traditional processes have restrictions and limitations. So laser provides that advantage of giving the accuracy. So since there is no physical contact between the tool and the work, as we have seen, so the wastages are minimum and post processing and maintenance of the machines are limited. So the process produces object of very high precision and accuracy, because the cutting of the surfaces are very much precise in nature. So there is no extra material that is being removed, or there is no overcut in case of laser, because the thickness of the lasing ray or the beam of laser can be 1/100 of the diameter of our hair. The diameter of the lasing ray or the beam that can be generated is to the tune of 1/100 of one single strand of our hair. That much precision is possible over here with the help of laser. So in space research, in nuclear, automobile, mainly in our field, we can say that laser is having an immense potential, okay, of its applications. Disadvantage is the cost. Cost factor is very high and trained workers are to be used over here. A skilled labor is required. These two are the limitations, and rest is not a limitation. But nowadays, value for money is there, so cost is not a disadvantage to be very frank. Okay? Because value for money is there in this machine. So we can ignore cost, but we cannot ignore the skilled labor. The machining and the operation of the machines need a skilled labor. So that might be one of the disadvantages. Applications are tremendous anywhere. You find application of laser is there, right from medical to space research. So sky is the limit for laser. Any application you find, there can be laser in mechanical, in civil, okay, in space research. Anywhere you will find laser as its application. It has penetrated to multifaceted domain of technology. Aerospace, defense, composite machining, automotive industry, electronics, medical, nuclear, micro machining, everywhere you find this application of laser. And because of its potential, it has been accepted or it is being used nowadays more and more. So these are some of the products that can be used in machining. Right from micro level to macro level, you will find the machining is being done. 100 micron wide deep hoods have been created over there. These are the same images that have been taken. Okay, so cutting of 25 micron thick polyimide. This one 900 micron thick silicon sheet gasket being used. Okay, so high precision. High speed drilling of 20 micron hole in 50 micron thick foil. This is also another same image that has been taken. Cutting of 1 millimeter tube with the laser rays. Okay. Thank you. Any questions?